Hey guys, welcome to 6.6 Enthalpy. The heat evolved in a chemical reaction. So first off, we're going to start by defining what enthalpy is. Enthalpy is the sum of its internal energy and the product of its pressure and volume. Basically, what that's going to tell us is, as you can see, this reaction or this formula right here looks very familiar to us. H is going to be our enthalpy. E, remember, is our internal energy, and P times V is pressure and volume, obviously. Enthalpy is a state function, and what does it mean to be a state function? A state function means that we don't need to know how it got there. All it matters is its current state. So all we care about is its current state. That's all we care. It doesn't matter how it got there. And as you recall from our last section, 6.5, we kind of said we were going to skip some steps, and we're still doing that. And so we're going to always say that our pressure is at constant pressure, which means that leaves us with delta H, or change in H. Remember, delta means change, right? So we're talking about change in enthalpy is going to be equal to our heat, and we're talking about that being at constant pressure, like I said before. So in terms of endothermic reactions and exothermic reactions, this has the exact same signs as Q at those points, but delta H, as you'll see as we move through this course, is going to become more important for that than Q. So endothermics, remember, have a positive Q, so they have a positive delta H, and these guys are absorbing energy. So they're absorbing energy. These are ones that feel cool to the touch, right? When you touch it, it feels cool. An example of this is like those instant ice packs. You break them open, the chemicals mix, and you have an endothermic reaction. So it is absorbing energy or absorbing heat, depending on if you want to define it like that. Then we move to our exothermic reaction, which is going to have a negative delta H, or a negative change in enthalpy. And this is where we're releasing energy. And this one will feel hot to the touch or warm to the touch. An example of this is those hand warmers, as we talked about in the opening of this section or of this unit. So we have an example right here, example 6.6. We're supposed to identify each process as endothermic or exothermic, and we're supposed to indicate the sign of delta H. So sweat evaporating from the skin. I'll give you a second to think about it. Sweat evaporating from the skin is going to be endothermic. Endothermic. And so delta H's sign will be positive. The skin must supply the heat to have the perspiration in order for it to continue to evaporate. So we're like, and it also feels cool to the touch if you feel like the reason you sweat is so you can cool your body down a little bit, and that's exactly what's happening. What about water freezing in a freezer? Water freezing in a freezer is kind of weird to think about, but it's actually exothermic. And the reason that is, delta H is going to be negative. The reason that is that when water freezes in a freezer, heat has to be released so it can cool down enough so it can freeze. So that's a way to think of that one. Wood burning in a fire, this one's hopefully pretty simple, probably the easiest one of all three, and that is exothermic, because this one is just easy to visualize, and so delta H is going to be negative. So that's one thing that you can use this for, but obviously we're going to go a little more in depth with that. Now if we move on to the molecular level, we're going to talk about why endothermic and exothermic reactions happen. So remember, always remember, that when bonds break, energy is absorbed. So it takes energy for us to break bonds. So how are reactions exothermic and endothermic? Well, in an exothermic reaction, we have weak bonds. and they're breaking, and stronger bonds form. So only a little amount of energy is used to break the bond. So we don't use that much energy, and the strong bonds are formed. So lots of energy is released. And so basically we have like a net release of energy is a way to think of it. Then if we have endothermic reactions, this is where we have strong bonds breaking and weak ones forming. So this is going to be a net absorbing of energy. Now this is kind of all background, and the key here in this section, the one that we're going to use probably most often, is the stoichiometry behind delta H. Stoichiometry behind delta H. So we know that delta H of a reaction is the enthalpy of a reaction. That's just kind of a way of it abbreviating Rxn. In chemistry, we should hopefully know always means reaction. So what type of property depends on how much you have? This is now like the third time I've asked you this question. This is an extensive property. Remember, that means how much you have. Extensive property. So let's talk about what that means. So below we have a reaction, and in that reaction we have something new in that reaction that we've maybe never seen before, is this delta H is negative 2044 kilojoules. And what that means is when I burn 1 mole of propane, C3H8, I get that many kilojoules of energy. So when I burn 2 moles of propane, I would get exactly right, twice that much energy there. And so we're going to actually get to use that in an example problem down below here. But remember, it's based on the stoichiometry or on the multiple ratios, if you want to call it that. And remember, our multiple ratios are the numbers that are out front here. Granted, when there's nothing out front, remember we call that 1. So let's look at this reaction here. Stoichiometry involving H. So we have an LP gas tank in a home barbecue. It contains 13.2 kilograms of propane, which I forgot to write in my letters there, C3H8. Calculate the heat in kilojoules associated with the complete combustion of all the propane in the tank. So basically, we're trying to figure out how much energy we can get from 13.2 kilograms. So let's go ahead and jump right in. We're going to set it up just like all the other stoichiometry problems we've done in our lives. So we're going to start with 13.2 kilograms of propane, C3H8. And I'm going to put it on my T-chart here. And the first thing that we have to do is we have to go from grams or kilograms to grams. We know that 1 kilogram equals 1,000 grams. This gets us from kilograms to grams. And now we can go from grams to moles by dividing by the molar mass. If we went through it, the molar mass of propane is 44.09 grams of C3H8. And that's equal to 1 mole of C3H8. And remember how we found that is we took 3 times 12, which is carbon's atomic mass, plus 8 hydrogens, which are about 1. So that gives us right around 44. Now we get to use our balanced chemical equation at this point to solve. We know that for every mole of C3H8, this 1 mole came from up here where this is understood to be 1. Every time we burn 1 mole of C3H8, we evolve this much energy. So on top, we're going to put negative 2044 kilojoules. And that will actually be our answer. And remember, when we're solving these problems, we multiply across the top. So in our calculator, we'll take 13.2 times 1,000 times negative 2044. And we'll divide that by 44.09. Then we'll hit equals in our calculator. And with sig figs, this should come out to be negative 61,500. I lied. It should come out to be negative 615,000,000, and that's kilojoules. So that's quite a bit of energy that you're getting from one tank of propane to barbecue. All right, thanks. See you next time.